Hello, welcome to the Aston Martin Cognizant Formula One Team Factory. The factory is located in Silverstone, UK. We are literally right across the road from the historic Silverstone circuit, and we're the only F1 team to be located right next to a circuit itself. Back to the facility itself. Now, we've been operating out of here since 1991, and the team started with 35 employees, and the number currently stands at 550. And the factory has developed and evolved with us over the past 30 years. Let's take a look around. Over 3 decades, the technology in the sport has vastly changed. 30 years ago, we had just started using computers. There was no cloud, and the idea of remote work was something that hadn't crossed anyone's minds. 30 years later, we live in a digitally transformed world where automotive manufacturing and racing is as dependent on technology as the people. Today, securing our digital footprint against cyber attacks is a crucial and vital component to ensuring a successful organisation. Now, what does it take to build an F1 car? Let's go and have a look around. So, from the design office to the model build, this is the first time that the car takes its step into the real world off the computer screen, but only at model size. Now, Ronnie here is the model build technician. He's going to tell us a little bit more about this 60% model, which presumably will make its way to the wind tunnel.
It will. We use the wind tunnel model basically to correlate what we do in CFD. As you say, it's the first time that it's a real physical product. We do this just to actually check that things are going to work, it's going to go in the direction we think it will, and to make sure that nothing is going to break, basically.
So why not just put a full-size car into the tunnel?
Currently, the FIA say we're only allowed a 60% size wind tunnel model, so that's what we do. All the teams are running 60% now. It's still an efficient way. The bigger it is, the closer the correlation to a full-size car. Yeah. As I say, we're only allowed 60%, so that is literally the only reason. And the physical size of the parts would be so big, the wind tunnel then obviously has to be a much bigger as well.
And costs would go up,
and costs would go up, etc. And yeah.
So the car is covered in sensors that
is.
feed back information in the wind tunnel. Talk us through that process.
Okay, so the car itself is actually static, but it's on a physical rolling road. So the wheels are rotating approximately 40 meters per second. We can simulate lift, drag, we can steer the car, we can yaw the car to the wind as well. Basically, we can simulate everything that happens on the full-size racetrack.
Wow.
And we can obviously measure the load, etc., as just the same as you can on the real car.
And then watch the wind's journey, and that's what creates these licks and shapes, isn't it?
Exactly, every single part on here is, as you say, it's shaped because of the way the wind is going. We're trying to make it as efficient as possible and to create as much downforce with as little drag as we possibly can.
So you must constantly be evolving parts.
Absolutely, every single week, every time we test, you'll find something new at the front which might upset something at the rear, so then you have to change something at the rear which then might upset something at the front, and the process just carries on. It's a constant evolution every time we test.
My goodness. So what would be the man hours to create a model like this?
I think probably last time we made one, it was approximately 70 days for 2 people, and that's probably 10 to 12 hour days, and that's just to get it to a physical shape. That's not including any production time, that's just us fitting it together.
So what's the next part of the journey then for this?
So after we found a direction we want to go in, so the aerodynamicists would then probably exploit that area. So then you would physically hand over the data to full size, and then the production would start again. They would probably make a physical component, and then eventually it'd make it onto the race car.
Wow.
And then it would be going around the track.
So this is literally one big full factory, isn't it, in itself?
Exactly that. Everything that you have on a full-size car, we have exactly the same. Us model build technicians are the equivalent of the race team. It's exactly the same. And
now we find ourselves in the simulator. Now, pre-race, we run thousands of hours in the simulator to find the best advantages and disadvantages and different setups of the car. Now the driver sits in this replica of our car and looks over at their 180-degree screen, but this isn't about the driver learning the racetrack. They're pretty good at that themselves. This is about trying different setups for optimum performance. Electronics. This is the department that literally touches every area of the car. They create so much in here, including this. This is a harness. This sits underneath the driver's seat and is essentially the backbone of the car. It feeds off sensors like vanes, 150 sensors that then feed back to the pit wall at around 3,740 gigabytes of data per car per race weekend. Another vital part of the car that uses electronics is, of course, the steering wheel. And Jed, sir, is going to tell us about the design process from beginning to end when a driver joins the team.
Basically, they come in with their own designs, really, of what they would want on a wheel. That's then built as a prototype, which is used on the simulator. The wheel is then built and designed around them, used at pre-season testing, and then from there on, they then have tweaks they like to put in and everything else, and the wheel's built accordingly.
So what sort of personal choices do they have?
They have different switches in different places, different functions, and the grips as well, the handles and so on. The rotaries, which decide certain parts of the wheel, they're all different.
How long would the process normally take?
Anything from 2 weeks up to a month, really.
So here we are in fabrication, the fab shop, and I am going to have a chat to Dave, who's been here for 21 years. You're part of the furniture, Dave.
Yes, I am, yes.
So tell me what happens in the fab shop.
So in here we predominantly make all the parts for cooling the engine. So water radiator, oil cooler, charge air cooler.
I love the fact that over the last 21 years, every radiator has been touched by you.
Yes, I've just about made every single oil cooler and water radiator that's been on the car.
What's this?
So this is an oil and water radiator. So you've got water this end and oil this end. So I make the oil part first and then go on to the water.
So where would this sit on the car?
So if I was a driver, this one is on my right hand side.
Right.
And then the charge air cooler, which is over there, will sit on that side of the car.
Okay, and that's not changed over the years,
No,
has
they've
it?
always been in the side pods.
And how long would it take for something like this to be made?
Overall, it's about a 2-week job.
And how much does that cost?
Our part is probably around £30,000, I'd say.
No.
But when it's completed, maybe 40,000.
And how many per year would be used?
That's number 14.
14?
Yeah, so we're going to have 18. So it's usually between 14 and 22 a year, depending on how many get damaged. These three here show the progression through the years of how the designs change. Almost 45 degrees. This was a little bit less, but leant over. And then this is almost parallel in the car.
How fascinating. Yeah. But the fundamental, that sort of honeycomb effect,
yeah,
doesn't seem to have changed so much.
Yeah, pretty much stayed the same.
Now, I'm quite intrigued by this one, because this
Yes.
doesn't look so healthy.
Yeah, so that's nice and flat, and this is quite curved. So the ones we make now are curved, but on purpose. This is curved after a shunt. Obviously, that's well damaged. And this was damaged in Japan in 2010 on Liutz's car. He was hit by Massa.
Massa.
Yes. And that was the first lap of the race as well, first corner. And then this one, this is off Paul di Resta's car at Spa in 2010. And he was hit from the side, and that's the imprint of the wheel rim from the other car. But the cooler actually finished the race like that.
No.
Yeah, although you can see how squashed it is. It's amazing it ever worked, but it did.
So talk me through the process of fabrication then.
About 6 years ago, before that, we made everything by hand basically. So all these tanks here are made by hand, which is basically knocking them over a block like this. We'll just hammer away and get the shape to it.
Until 6 years ago.
Up until 6 years ago, yes. And then slowly but surely, other methods of producing these tanks have come along. So machining now, this is a machine tank. And we just couldn't achieve that shape by hand. And the other process that, although we haven't got it at the moment, is 3D printing.
How times have changed.
Yes, I know.
Well, Dave, thank you very much.
Yeah.
Machining is where we're heading to next.
Okay, thank you.
This is our newest facility. This is the machine shop. Now, when every car is a prototype, you have to make everything in-house. You can make an awful lot by hand, but when you start bringing in some complex machinery, you can start making some very sophisticated pieces of equipment. Vas, the machine shop, you have some incredible machines out there. What components are you making in here?
The majority of the components we make can be from any parts from the front wings, rear wings, floor, fuel systems, cooling systems, even up to the steering wheel.
And how long might it take? I imagine they take different times for different things.
Well, some parts can take up to 14, 16 hours, and some of them can take just 5 or 10 minutes. So it depends on the actual features on them and the size as well. The majority of the materials we use are aluminium alloys, steels, stainless steels, titanium, and even some plastics.
Okay, so can you explain to me from design to stores?
We'll start over here with the programmers. They'll get the paperwork for the actual part, and they'll use the 3D model which has been made by the designers to generate a program. Initially they'll choose which is the right machine to manufacture that component, depending on the features that component has. And then they'll program it offline, they'll send us the program, we'll physically make the part, manufacture it, briefly inspect it, everything's right to the drawing, and then it will go to inspection where it's going to get 100% checked, and then from there it goes to stores or straight on the car.
Now, in addition to our machining and composite facilities, we also have ADM, Advanced Digital Manufacturing. In layman's terms, 3D printing. So why would parts be manufactured here and not at the other facilities?
So it's a question of what are the advantages of 3D printing over traditional manufacturing. So it can be cheaper once you've made the investment in the machinery. So the machinery is expensive, but then once you get down to component level, it can be cheaper. And we have the ability to make infinitely organic shapes, whereas we can be a bit limited by, with traditional methods, can we get the milling cutter into this corner and things like that, whereas we can print absolutely any shape we like.
So this is obviously new technology that presumably is going to become more and more important and a bigger part of our future in our sport.
Yes, absolutely. Additive manufacturing as a whole, there's a lot of investment across industry, investment in materials, investment in improving the technology, the reliability, the accuracy, the resolution. So all of these things are ongoing, and every few months you'll see quite big improvements. For DMLS in particular, we're all very excited about that. We think that is really the future of manufacturing. We think it will, certainly for now, it already treads on the toes of CNC machining, but we think in the future it could well supersede CNC machining and probably not make it redundant, but sort of heading that way, I would say.
Next up, we have laminating. This is the carbon fibre workshop, and 80% of the race car is made up of carbon fibre, which is an incredible material. It's very, very strong and incredibly light. Mark's going to tell us more.
Hiya.
So, carbon fibre.
Yes, so this is, like I heard you say, majority of the car is made up of carbon fibre, mainly for its strength and durability and the fact how light it is.
There are lots of different types of carbon fibre, aren't there?
Yes.
So talk us through that.
So you'll have bits of carbon fibre all over the car. The rear end of the car sees a lot of heat, so we use a high temp carbon fibre that can sustain its shape up to 200-300 degrees. Front of the car, the heat isn't an issue, but it might be the strength. We might need to use a Kevlar for the stone chips to protect the front wing, protect the noses. We have Xylon that sits down the side of the car. That's to protect the driver during an impact. So we have these big Xylon panels sitting either side of the car. So they'll help us keep him safe. And there's lightweight material just for internal panels for bodywork, which is literally just to create a shape, an aero shape, but not for any structural purpose whatsoever.
So how long would it take to make a nose cone, for example?
Nose cone, probably 2 guys working 24 hours a day. We're looking probably about a week's process just for one nose.
So, Mark, you talk us through the carbon fibre process, and then parts are then vacuum packed and brought down here, aren't they, to the autoclave. So what happens?
So everything's brought down. Obviously this is quite one of our smallest autoclaves for smaller components, so they'll be put in there, be put onto a vac. One is a vacuum, we'll pull a vacuum out there. The other one is a sensor, so if there's any problems while it's in cure and the door's locked and we can't see it, we'll know if there's been any problems during the cure. So everything is censored. We'll close it up and then it will be put on normally a 2-hour cure of 135 degrees at 75 psi of pressure. It will be cured, then let it totally cool down, and then we'll bring it back out, we'll debag it and get the component out.
Next up, once cured, each component will then travel to the trim shop where they're removed from their mould and then trimmed down to their specification according to the design. Over 12,000 components will make this journey over the course of a year. This all looks very interesting, so what happens in here?
This is the inspection department. We check every component that goes into the manufacture of the car to make sure it falls within the designer specification. And anything that's outside of it will either be concessed by the designer or it goes back to the supplier for rectification or replacement.
And how do you inspect them?
We use several different pieces of kit in here. We've got a laser scanner here which allows us to scan the part and then do a best fit against the designer's model to make sure it falls within the specification. And we also use a couple of machines down the end there to do a lot more critical work, which is tighter tolerance. And we've also got various pieces of kit like gauges and micrometers and verniers and thread gauges.
Okay, and so how many parts would you see in here over a day?
During the car build, we would probably see about 500 a day, 500 parts, different parts. Yeah, it's quite a busy time over the 3 months of the car build.
Amazing. And so from here, then what happens?
From this point, once the part is accepted, it will go through, we'll save the reports, save the records of the inspection, goes into the stores and then gets issued out for production to either the comps department or the race team, and then away it goes to the circuit.
NDT, non-destructive testing. All of the parts travel through this department before they're added to the car.
Well, we use 3 methods basically. One is ultrasound technology, which is using high frequency sound to penetrate inside typically carbon components like the suspension, which is like this screen over here. And then the second one is dye penetrant, which uses a fluorescent dye, which we coat the components in, then we wash it off, and then we inspect it under fluorescent light conditions, and any imperfections will show out on the surface of the component. The disadvantage of that is that you can only detect surface components, surface cracks, sorry. You can't detect anything internal. So the ultrasound is a better method for doing that because you can see inside. And the third method is fluorescent magnetic particles, which is a process whereby it's very quick. You use a magnetic dye, you energize it with electrical current, that uses, which generates a magnetic field. That magnetic field then brings the magnetic particles to where the crack is, and it shows up in a very similar way to the penetrant does under fluorescent conditions. But it's a very quick method. The disadvantage of that is you can only use it with ferrous materials, so anything that's magnetic, so drive shafts, things like that, nuts and bolts.
Now, once the parts have been manufactured, they then move here to sub-assembly before then going to the track for full assembly. And Alistair is going to tell us more.
So in sub-assembly, we get all the components back from the track or new components. We strip them down if necessary, clean them, check everything over, and then reassemble it, ready to go back to the car.
So what sort of parts will be coming through here?
So we do the uprights, we do the drive shafts, we do steering columns, pedals, fuel collectors, wishbones, we change the bearings on. There's a lot of components that come through here that just go directly to the race crew.
And they're serviced and sub-assembled here?
Yes.
When in the year then is your busiest time?
So the build up to the first test is normally quite busy because the parts come quite late. And then after that, it's normally between the triple headers when you've got limited time, especially with flyaways, where you get the bits on a Tuesday afternoon and they've got to go by Friday. So you've got a short amount of time to get everything turned around.
And how do they then go from here to the track?
So when they come back, we put them back into their pack horses and we give them to our logistics department and they organise which shipment they're going to go on back to the track.
When you're watching an F1 race, you'll hear one very calm, very controlled voice speaking to the driver. That's the race engineer transmitting information from the pit wall. But behind that voice is an army of people working not only on the track, but also back here in mission control. So, Ollie, can you talk us through that, how it all works?
Within mission control, we have access to all the same data they have at the circuit, all the same timing, video feeds and obviously on-car data. We have the same intercom and radio panels they have at the circuit. Our role really is to support as much as we can in the information feeding to the pit wall. Within our main mission control, we have strategists feeding information on other drivers, traffic situations, and obviously the race situation as we go on. There's also a lot of performance feedback for the car data, as well as specific error report and competitor analysis.
So how many people would you have back here at base?
So in total around 20 through an event, giving various feedback on all aspects.
Speaking to how many people on trackside?
Probably 6 on the pit wall, plus a lot of others in the garage, just feeding back on all the additional work that and analysis that gets done.
Racing today is a technology-driven data problem, and the question that we must ask ourselves at all times is, are we securely and safely securing our data? Sentinel-1 is our cybersecurity partner that ensures our mission-critical data and the devices and cloud upon which our data resides is secure from cyber attacks. During the off-season, this area is the hive of activity. It's the heart of the factory. When F1 isn't on your screens, it doesn't mean it's sleeping, it means it's busier than ever. This is like a spotless garage where all of the parts are finally assembled and the cars go out to the first race. 35,000 CAD drawings, 13,000 individual components, 750 litres of green paint, 550 staff, 2 cars, 1 team, and that is how you build an F1 car.